So in this paper, like, we are going to implement the double MAC for a DSP application. So this is also will help to convolution neural network. Also we are going to make a MAC architecture, that is multiply and accumulator architecture. So in this multiply and accumulator architecture, we are making one new thing. So what is that? In the sense, like, we are going to introduce the floating point numbers also here. So using that floating point multiplier design, we are going to implement this complete architecture. So here we are giving the two inputs like A and B and M and C value, and based on that we will be getting the output of the M. So this is the double MAC architecture. Normally we can use the normal multipliers and adders and all. So based on that we can implement the CNN layers. This is the CNN layer for our architecture. We can implement in this way. So but we need to do something in an efficient way. So for it will be it need to help for the digital signal processing application also. So for that purpose we are including into the IEEE 754 floating point numbers. In that especially we are using the double precision floating point numbers. So using that we will be implementing the architecture. So for that purpose I am preparing the synopsis here. So in the synopsis, like, we are mentioned like everything. So the main objective we are explained here of introduction, existing system, and as well as the proposed, everything we explained here. So this is the proposed block diagram for us. So this is like actually the base paper was implemented with the help of the normal multiplier only. So that is double MAC in the sense this is the B into C, A into C. You will be giving the two inputs A, B and C. So A need to be multiplied by B and as well as B need to be multiplied by C, and both the results will be getting into the main output. So that main output like A, B, C, whatever the results what we will get like A, B, C, it will be getting as output, and the Gaussian bit will be added in the center of the data. So based on that we will be implementing the CNN architecture also. So based on the CNN architecture we will be showing the output here. So now I am showing the simulation results for that. So for that purpose I am using this MAC architecture. So in this MAC architecture we are making with a single precision double precision floating point number. Floating point number in the sense it will be comes around 64 bit. So based on that we will be doing this process. So here the MAC architecture we are explaining here. This inside the MAC architecture, that floating point multiplier double will be there. So I am just using the MAC architecture here. So the MAC architecture we need to give the input in the 64 bit of floating point number. So you can take like any number. So for that purpose, like, we are using the floating point. Using this online calculators we can convert the normal numbers into the floating point numbers. Floating point numbers, like, this is IEEE 754 floating point numbers. Like, we can give the fractional numbers here and we can convert it into easy way. So in bottom you can able to see binary 16, 32, 64. Now we are going to do for 64 bit only. So you can give like whatever the number you wanted, like 50 into 50.2 or something, whatever the thing you wanted you can give. And another one data you should give, so 10.5 I am giving. So this is like whatever the operation, for example addition in the sense we can check it like addition, multiplication, subtraction, multiplication, division, everything we can check it here. I'm just going to give the same input here. So this is the input. Now we need to copy. So just copy this value and you can feed into here. So right click, add to wave all items region and below. You'll be getting the waveform here for the MAC architecture. So in this multiplier we should give the input. So clock will be the normal clock and clock, and reset will be the normal, like reset initially it should be 1, make it as a 1, and data in coefficient data we should give, right click and force, and you can give the first value. So this is the 64 bit binary value we are giving here, and second value you should copy the second value. So this is the binary value of that, 10.5. you can copy that value and you can give it here, and then you can run it. So now the reset condition is high, so the output will be the 0 only. So once you just change the reset, so based on the reset the output will come to us. So MAC in the sense multiplier accumulator circuit, so it will be just doing the multiplication plus addition. So we can verify the both. So the paper topic, they are talking about only the multiplier, but we are implementing the adders also, that is floating point adder also we are implementing. So now you can convert the values into the hexadecimal. How we can able to verify that? In the sense, we can easily verify here. This is the input like 50 and 10, and the results we got it here in the hexadecimal format. What we can get it, you can see here 404E59. So based on that we will get it. You can see here, this is the product output 408078. So this is the product output. So previously I'm just clicking the addition. Now we need to do the addition multiplication. First MAC operation will perform the multiplier operation. So that multiplier results, it came here 4087 CCD. So this output will be added with again the same output, that looped one, that 4080, that is for same value will be added again. So that added value will be here. So this is the first output. This value will be added with the 0, and it will be providing the output of the product. And then this value and this value need to be added, and it will be giving the output here. So we can check it here. So this result only need to be added again and again. So that is 2 value we need to add. So you can see here the 409078, same value we will get it from here, 40989078 CC value. So like this you will be getting the continuous addition results of the 2 multiplied results. So this is the MAC operator based on the double precision floating point multiplier, and according to our idea we made it. So that design I will show you. So in this part we will be having the FP multiplier. For that we will be making the C logic, and based on the C logic, the registers and C logic will be helped to make the floating point multiplier double, and then based on that we will be implementing the MAC architecture. So this is the simulation part, we done it. So I'm just preparing the final documentations for that complete project. So here the explanations and all will be there: abstract, introduction, literature survey, model separation, everything, that each and every model explanation and the results, everything will be added in the report. So in this part, end of the report, we will be adding the results of the project also. So this is the device utilization summary. It's a area calculation for that project, and delay also we calculated, and the comparison table we made it with the help of the comparison between the existing multipliers. So based on the existing multipliers also we are doing the comparison, and this is the complete work of this project. The future enhancement is nothing but that MAC operation. We are providing the services for these things under, like source code explanation, documentation, online sessions, and everything will make it for you people. So this is our domain, specialized domain for us, and this, thank you.